Dear friends, hello. Today in this lecture, we will learn about the data link layer of OSI reference model. First of all, please see the contents which I shall cover. I shall take up different functions of data link layer like framing, error control and flow control. As we know, process of communication is very complex. So, the communication protocols are divided into 7 layers. These layers are defined by ISO OSI reference model and data link layer is layer 2 from bottom in this model. It is responsible for communication between adjacent network nodes. It handles the data moving in and out across the physical layer. Data link layer is divided into 2 sub layers, the logical link control and medium access control. Logical link control part of data link layer handles framing, error control and flow control, whereas medium access control layer handles the channel management part. Now, we will discuss framing, error control and flow control part of data link layer. First, we will start with framing. As we know, physical layer is only responsible for communication of raw bits received from data link layer of source computer to destination computer. There are multi-million bits that need to be transmitted for transferring a simple file. There are always chances of bits getting mixed up or some error due to change in sequence of bits. In order to solve this problem, stream of bits are divided into frames. Now, what are the methods of framing the bits? There are 3 methods which are commonly used for framing, which are character count, byte stuffing and bit stuffing. The first framing method, that is character count method, uses a field in the header to specify the number of characters in the frame. When the data link layer at the destination sees the character count, it knows how many characters follow and also can come to know where the frame will end. Please look at the figure. There are 4 frames in this figure with size 5, 5, 8 and 8. As you can see, first frame has data A, H, 7 and 8. There is only one problem with this method. The count can be garbled by a transmission error. Just look at the figure. If the character count of 5 in the second frame becomes 7, the destination will get out of synchronization and will be unable to locate the start of the next frame. For this reason, the character count method is rarely used nowadays. The second framing method is flag bytes insertion using byte stuffing. This is also referred to as character stuffing. Just see to the figure. ASCII characters are used as framing delimiters, for example, DLE STX and DLE ETX. The problem occurs when these character patterns occurs within the data. Solution to this problem is to stuff an extra DLE into the data stream just before each occurrence of an accidental DLE in the data stream. The data link layer on the receiving end unstuff the DLE before giving the data to the network layer as shown in this figure. The flag byte DLE and STX are inserted at the start and DLE ETX bytes are inserted in the end. The problem with this technique is it is closely tied to a use of 8-bit character. So, in order to remove this problem, a new technique has been developed to allow arbitrary size character. This method is called bit stuffing. In this method, each frame begins and ends with a special bit pattern called a flag byte, which is 0, 1, 1, 1, 1, 1, 1, 0. Please see the figure for bit stuffing. In this technique, there is a possibility that this particular pattern of 0, 1, 1, 1, 1, 1, 1, 0 may appear in data itself. In order to take care of this problem, whenever sender data link layer encounters 5 consecutive ones in the data stream, it automatically stuffs a 0 bit into the outgoing stream. When the receiver sees 5 consecutive incoming ones followed by a 0 bit, it automatically de-stuffs the 0 bit before sending the data to the network layer. So, this was about framing part. Now we will move on to error control. In data communication, error detection and correction are techniques that enable reliable delivery of digital data over unreliable communication channels. Error control is the process of detecting and correcting both the bit level and packet level errors. There are two types of errors: single bit error and burst error. The term single bit error means that only one bit of the data unit was changed from 1 to 0 or 0 to 1. In the figure shown, 0 bit is changed into 1. Burst error means that 2 or more bits in the data unit are changed. Burst error is also called packet level error, where errors like packet loss, duplication, reordering takes place. In figure shown, please notice that 3 zeros are converted into 1. This is burst error. There are 3 basic types of error detection techniques: parity checking, cyclic redundancy check (CRC), and checksum. In parity checking, a single bit is added that indicates whether the number of one bit in the preceding data is even or odd. If a single bit is changed in transmission, the message will change parity and the error can be detected at this point. Parity checking is not very robust, since if the number of bits changed is even, the check bit will be invalid and the error will not be detected. In single bit parity checking, parity is checked by adding one additional bit so that total number of ones become even. Please see the table for single bit parity checking. Here, even parity method is used, in which total number of ones are made even by adding one additional bit. Data word is original data and code word are transmitted data with parity bit. Parity method for error detection is very simple method, but it cannot correct the error. Moreover, parity does not indicate which bit contained the error even when it can detect it. The data must be discarded entirely and retransmitted from scratch. Next method for error detection is cyclic redundancy check. Cyclic redundancy check is a very efficient redundancy checking technique. It is based on binary division of the data unit, the remainder of which is added to the data unit and sent to the receiver. The receiver divides data unit by the same divisor. If the remainder is 0, then data unit is accepted and passed up the protocol stack. Otherwise, it is considered as having been corrupted in transit and the packet is dropped. Sequential steps in CRC are explained with figure as shown. Transmitter and receiver both should agree upon a standard generator polynomial, for example x cube plus x plus 1, which is represented as 1 0 1 1, a 3-degree polynomial. If we want to transmit data 1 0 0 1, then 3 zeros are appended to this data. Now it becomes 1 0 0 1 0 0 0. This data at transmitter side is divided by divisor 1 0 1 1. By performing this division, we get remainder as 1 1 0. Now this remainder is appended to the original data 1 0 0 1 and original data becomes 1 0 0 1 1 1 0, which is transmitted. On receiver side, data received is once again divided by 1 0 1 1. Please see diagram in which left side shows that data is received with no error and right side shows that data is received with error. In case there is no error, then remainder will be 0, which is shown on left side, and in this case data word is accepted. In case there is error, remainder will not come out to be 0, which shows that there is error and data word is discarded. Checksum is the third method for error detection mechanism. In the checksum mechanism, checksum generation is performed at transmitter side. Sender generates checksum. First data unit is divided into equal segments of 8 units. Then all segments are added together using 1's complement. Then result is complemented. It becomes checksum which is sent along with the data unit. Example is explained in figure. Suppose the following block of 16 bits is to be sent using a checksum of 8 bits. The numbers are added using 1's complement. We get sum as 1 1 1 0 0 0 1 0. Checksum is complement of sum which is 0 0 0 1 1 1 0 1. The pattern sent is 1 0 1 0 1 0 0 1 0 0 1 1 1 0 0 1 0 0 0 1 1 1 0 1, which is original data plus checksum. Now on receiver side, the receiver receives the data unit and divides into segments of equal size. All segments are added using 1's complement. See figure. Now suppose the receiver receives the pattern sent and there is no error. The result is complemented once again. If the result is 0, data will be accepted, otherwise rejected. If final data is non-zero, it is rejected. When the receiver adds the 3 sections, it will get all 1's, which after complementing is all zeros and shows that there is no error. We can see that sum is 1 1 1 1 1 1 1 1 and complement of this sum is 0 0 0 0 0 0 0 0, means that pattern is okay. Now take another case that there is a burst error of 5 bits as shown in figure. When the receiver adds the 3 bytes, it gets partial sum as 1 1 1 0 0 0 1 0 1 with carry as 1. So the sum is 1 1 0 0 0 1 1 0 and its complement is 0 0 1 1 1 0 0 1, which is not 0, and hence shows that pattern is corrupted. This is how we check presence or absence of error using checksum mechanism. Now let us move over to flow control. Flow control is one important design issue for the data link layer that controls the flow of data between sender and receiver. This problem may arise if sender sends data at higher rate and receiver is too sluggish to support that data rate. There are two types of flow control as shown in table: stop and wait protocol and sliding window protocol. Sliding window protocol has three types, which are 1-bit sliding window protocol, protocol using go back N, protocol using selective repeat. Now let us take simplex stop and wait protocol. In this protocol, we take the following assumption: the sender simply sends data and waits for the acknowledgement from the receiver. That's why it is called stop and wait protocol. This type of flow control is not so much efficient, but it is simplest way of flow control. In this scheme, we assume that communication channel is error free, but if the channel has some errors, then receiver will not be able to get the correct data from sender. So it will not be possible for sender to send the next data, as it will not get acknowledgement from the receiver. So it will end the communication. In stop and wait protocol, sender must wait for either positive acknowledgement from receiver or for timeout to send the next frame to receiver. So even if the sender is ready to send the new data, it cannot send. Sender is always dependent on the receiver. To solve this problem, sliding window protocol was introduced. In this, the sender and receiver both use buffer, so there is no necessity to wait for the sender to send the second data. It can send one after one without wait of the receiver's acknowledgement. And it also solved the problem of use of additional bandwidth for acknowledgement, as in this scheme both sender and receiver uses data frames for acknowledgement, and this process is called piggybacking. There are three types of sliding window protocols: 1-bit sliding window protocol, protocol using go back N, and protocol using selective repeat. Now let us take 1-bit sliding window protocol. In all sliding window protocols, transmitter and receiver maintains a window to keep track of data transmitted and data received. In 1-bit sliding window protocol, size of window is only 1 bit, means this protocol has window buffer size of 1 bit. So only possibility for sender and receiver to send and receive packet is 0 and 1. Since there is only 1 bit sliding window, so this protocol works like stop and wait protocol. After data transmission of any data, transmitter will wait for acknowledgement. Once acknowledgement is received, then only next data is transmitted. Next method is using go back N protocol. In this method, acknowledgements are used to acknowledge correct receiving of data. Receiver sends positive acknowledgement if frame arrived safe and in order. If the frames are damaged or out of order, receiver discard all subsequent frames until it receives the one it is expecting. The silence of the receiver causes the timer of the unacknowledged frame to expire. Then the sender resends all frames beginning with the one with the expired timer. For example, suppose the sender has sent frame 6, but the timer for frame 3 expires, means frame 3 has not been acknowledged. Then the sender goes back and sends frame 3, 4, 5 and 6 again. Thus it is called go back N protocol. The receiver does not have to acknowledge each frame received. It can send one cumulative acknowledgement for several frames. Please refer to diagram in which go back N protocol is used but with no error. So there is no need of retransmission. You can very well see that all the frames are received in time and accordingly acknowledgements are sent back to the transmitter. Now let us take a case when there is some problem with communication. See to the figure. In this figure, frames 0 and 1 are received and acknowledged, but there is a problem in transmission of frame 2. Frame 2 is lost on the way. So receiver will not acknowledge frame 2. When timeout will occur and still transmitter has not received acknowledgement for frame 2, transmitter will go back to frame 2 and will transmit frame 2, 3 and so on. Next we take up protocol using selective repeat protocol. Using go back N is good when the errors are rare, but if the line is poor, it wastes a lot of bandwidth on retransmitted frames. So to provide reliability, selective repeat protocol was introduced. When this technique is used, a bad frame that is received is discarded, but good frames received after it are buffered. When the sender times out, only the oldest unacknowledged frame is retransmitted as shown in figure. In this case, if second packet comes with error, then the receiver will accept the third packet, but it sends negative acknowledgement of 2 to the sender and buffer the third packet. Receiver do the same thing in fourth and fifth packet. When the sender receives the negative acknowledgement of second packet, it immediately sends the second packet to the receiver. After receiving the second packet, receiver sends the acknowledgement of fifth one as saying that it received up to 5 packets. So there is no need to resend third, fourth and fifth packet again. They are buffered in the receiver side. So this is flow control strategy using selective repeat. So in this lecture we studied about framing, error control and flow control strategies for data link layer. In framing we covered character count, byte stuffing and bit stuffing. Then in error control we covered 3 methods for detecting error, and those methods were parity check, CRC and checksum. In last, techniques for flow control were discussed. Thank you.